German engineers watch in silence as their wonder weapons humiliate themselves. February 1943, Sidi said, Tunisia, 40 degrees in the shade. One captured Sherman, 4.5 days, 350 kilometers, 0 breakdowns. Nearby German Tigers and Panthers limp, overheat, stall, demand constant nursing. The desert does not care about propaganda posters or kill claims. Germany's brilliant blueprints collapse where it matters most. Dust, distance, maintenance, ordinary drivers. If German engineering was supposedly superior, why did one dusty Sherman expose its most dangerous lie? Mid-February 1943, Sidi Zid, Tunisia. Heat shimmers above the desert track as a dust cloud approaches across the pale sand. An American M4, A1 Sherman rolls into view, its rounded hull coated in dust, its white star still visible beneath a freshly painted black German cross. The tank grinds to a halt. German officers from Schwerpanzerabteilung 501 gather around it, boots sinking into the sand, notebooks already open. This is War Daddy's second, captured intact during the fighting around Sidi Bouzid. Its engine idles steadily in the background, a low mechanical heartbeat that refuses to falter. The men circling it know they are looking at more than a battlefield trophy. They are looking at a problem. German crews are used to halts, to hatches opening, to mechanics dropping to their knees beside hot final drives. Here, the hatches stay closed. The engine note remains even. The tank simply waits. Over the next 4.5 days, a reconnaissance detachment drives War Daddy 2 across roughly 350 kilometers of North African terrain toward the port of Sfax. Sand, rock, rutted tracks, and broken ground pass beneath its tracks. The engine never overheats. The transmission never seizes. The final drives keep pulling with the same steady rhythm. German crews following in their own vehicles watch the American tank continue without complaint through conditions that often cripple their machines. Every kilometer contradicts assumptions about American industry. German doctrine has treated enemy tanks as crude, numerically overwhelming, and technically inferior. Yet this vehicle, built by Lima Locomotive Works and marked USS, a 3067664, behaves like a well-broken-in touring car. It keeps moving. Mechanical reliability becomes a strategic weapon. At Sfax, cranes lift War Daddy 2 onto a cargo ship. Chains tighten around its hull. The tank hangs briefly above the quay, then settles onto the deck for its journey north. Orders from the Heereswaffenamt are explicit. The vehicle must reach the proving ground at Kummersdorf intact and operational. Intelligence reports about American production have already reached Berlin, full of numbers and projections. Now, the numbers gain weight and steel. Spring 1943, Brandenburg. At the Kummersdorf Proving Ground, 25 kilometers south of Berlin, War Daddy 2 rolls off a rail car onto German soil. It now carries the designation Versuchsfahrzeug 259 and a Wehrmacht license plate, WH058941. Fresh white stencils cover its armor plates, marking thicknesses and angles in neat German script. The tank stands in a forest clearing of sand tracks, test hills, and concrete obstacles, surrounded by workshops and instrument sheds. Teams of engineers move in. They photograph every surface. They measure clearances with gauges and micrometers. They trace weld seams with gloved fingers, noting their simplicity. Where German tanks hide complexity beneath interlocking plates and intricate joints, the Sherman shows straightforward construction. Bolts, castings, and welds follow a logic shaped by mass production. The transmission draws immediate attention. German powertrain specialists remove covers and peer inside. They see herringbone gears, their teeth angled in opposing directions, distributing load across multiple contact points. In German factories, such gears are considered difficult to produce in quantity. German tanks rely on straight-cut gears, demanding precise tolerances and frequent adjustment. Their drivers learn double clutching and careful throttle work to avoid damage. The Sherman's gearbox offers 5 forward speeds and 1 reverse, with synchronization from 2nd through 5th. Gear changes become simple movements rather than delicate maneuvers. The Americans have designed a tank for ordinary drivers. Testing begins. War Daddy 2 moves through obstacle courses that mimic battlefield conditions. It climbs embankments, crosses ditches, and weaves through soft sand and hard-packed tracks. Engineers ride inside and on the hull, instruments strapped to brackets, pencils scratching on clipboards. They record fuel consumption, engine temperatures, and transmission behavior under varying loads. After each run, mechanics drain oil, remove covers, and inspect wear patterns. They look for scoring, pitting, and discoloration. They find smooth surfaces and even contact marks. Lubrication channels work as intended. Bearings show no early distress. The results undermine long-held beliefs about the trade-off between performance and reliability. The Sherman performs adequately in mobility and speed. It excels in endurance. The Continental R975 radial engine in this M4A1 becomes another revelation. It runs across temperature ranges that often trouble German engines. The cooling system, simple in layout, keeps temperatures within safe limits. Air filters handle dust and sand without constant cleaning. German crews in North Africa have fought clogged filters and overheating radiators. Every component reflects a philosophy that favors robust function over theoretical refinement. The tank is not elegant in the German sense. It is effective. June 6 and 7, 1943. Reichsminister Albert Speer arrives to oversee demonstrations. On the test slope, War Daddy 2 stands beside a brand-new Panther Osphron D and a massive Ferdinand tank destroyer. The lineup represents the cutting edge of German armored design and a single foreign intruder. Engine start. Exhaust fumes drift across the assembled officers. The Sherman moves first. It climbs the slope in a steady, unhurried ascent. The synchronized gearbox allows smooth shifts. The driver handles the vehicle with visible ease. The tank reaches the crest without drama and turns aside. The Panther follows. Its Maybach HL230 engine produces around 700 horsepower, nearly double the Sherman's output. The vehicle climbs the same slope and matches the Sherman's performance, but the movement appears more strained. Gear changes require more effort. The driver works harder to keep the tank in its power band. Then, the Ferdinand attempts the hill. At roughly 65 tons, with an advanced electric transmission, it represents German ambition in armored warfare. Halfway up, the heavy vehicle stalls. Its drive system fails under the load. Recovery crews move in, attaching cables and struggling to restart the machine while senior officers watch in silence. German prestige machines falter under public scrutiny. Speer later records his impressions. During an inspection tour in Italy in October 1944, he notes that reports on Sherman cross-country mobility are very favorable. He writes that the tank climbs mountains German experts had considered inaccessible to tanks. He attributes this to a powerful motor in proportion to weight and concludes that on level ground, the Sherman's mobility is definitely superior to German tanks. The 26th Panzer Division has reported this advantage directly. On June 27, 1943, Das Reich publishes a carefully worded article. It calls the Sherman one of the special accomplishments of North American laboratories and a praiseworthy product of the North American steel industry. It highlights serial construction and the fulfillment of what it describes as almost arrogant requirements of the North American automobile industry. It even notes the gyro-stabilized gun as a first attempt of its kind. Publicly, the tone remains controlled. Privately, concern spreads. Back at Kummersdorf, testing continues through summer and autumn 1943. Engineers push War Daddy 2 and other captured Shermans through extended range trials. They drive them for thousands of kilometers, logging every maintenance action. The data accumulates. Operational ranges exceed 2,000 kilometers before major overhauls become necessary. Early Panthers in field conditions often fail before 500 kilometers. Transmission efficiency measurements show lower power losses than any German tank. The synchronized gearbox reduces driver error. Clutch and gear teeth survive abuse that would cripple German systems. Final drives, built with the same herringbone principles, show almost no failures under loads that routinely destroy Panther final drives. Restoration projects decades later will find Sherman final drives still serviceable after long storage. The design margins prove far greater than immediate wartime needs. By late 1943, internal reports circulate through Wehrmacht technical branches and the Armaments Ministry. They describe an uncomfortable reality. American automotive engineering has reached a maturity that German industry lacks, despite its theoretical knowledge. Mass production tolerances that German engineers consider crude produce vehicles that function better in the field. Interchangeable parts allow quick repairs with basic tools. German tanks, built to tighter tolerances, demand factory-level precision for many tasks. The roots of this difference lie in pre-war society. In the United States, automobiles have become common across social classes. Civilian mechanics and drivers gain experience with complex vehicles in everyday life. In Germany, cars remain largely luxury items. The Volkswagen program, promised since 1934, has delivered fewer than 1,000 civilian vehicles by 1939. The result is a narrower base of automotive expertise. American tank design assumes conscript mechanics with civilian automotive backgrounds. German design assumes specialists with years of focused training. Field reports from 1943 and early 1944 reinforce the Kummersdorf findings. Panther units struggle with strict operating restrictions. Drivers receive orders to avoid frequent gear changes. Third gear fails so often that manuals warn against its use, except when absolutely necessary. Panthers must not turn while reversing, as this can destroy the transmission. Pivot turns are limited to conditions where ground resistance is equal on both tracks. Foreign objects in the running gear can jam the drive sprocket and immobilize the tank for hours. These limitations exist in vehicles built by skilled workers in dedicated factories. The Sherman follows a different path. Designed by engineers at General Motors, Ford, Chrysler, and other firms, it uses commercial components wherever possible. Multiple manufacturers build identical transmissions to shared specifications. Parts from Caterpillar, Buick, and Ford can mix freely. Standardization, routine in American industry, remains elusive in German tank production, where each factory introduces small variations. Through 1943 and 1944, more captured Shermans arrive at Kummersdorf. Others from Soviet formations on the Eastern Front. Engineers test Firefly variants with British 17-pounder guns. They note how easily the larger weapon fits into the Sherman turret ring. The original design has left room for growth. The Panther, rushed into service to counter the T-34, offers little capacity for major armament upgrades without extensive redesign. Reliability trials expand. Shermans run hundreds of kilometers cross-country under controlled observation. Every breakdown, however minor, enters the record. The results are compared with Panther and Tiger field data from the Eastern and Italian fronts. Patterns emerge. Panther operational readiness averages below 40% through most of 1943. Some units report 20 to 25% readiness. During Operation Citadel at Kursk, Panthers reach only 16% operational. Mechanical failures remove more tanks than enemy fire. By December 1943, readiness climbs to 37%. February 1944 remains at 37%. May finally records 78%. Even at their best, Panthers never match the availability Shermans achieved from the beginning. Engine life tells the same story. Sherman diesel variants routinely exceed 3,000 kilometers under proper maintenance. Improved Panther engines after extensive work reach 700 to 1,000 kilometers. German reports in March 1944 present this as success. In reality, it represents roughly one-third of Sherman diesel endurance. Sherman transmissions require little attention between overhauls. Panther transmissions demand constant care. Third gear failures become so common that drivers learn to skip directly from second to fourth. Sherman final drives endure conditions that destroy Panther final drives within 100 to 200 kilometers. German units that capture Shermans begin using them. Unlike Soviet T-34s, which often receive extensive modifications before German service, Shermans enter combat almost unchanged. They do not need fundamental corrections. They work as delivered. Reports from these units echo the Kummersdorf data. Crews note that Sherman operators can focus on tactics rather than nursing their machines. Panther and Tiger crews worry about simply reaching the battlefield and returning without breakdown. In some regiments, letters and after-action reports praise the American tank's reliability in plain, unadorned language. Behind the numbers are men who know that a missed gear change or a bad turn can decide whether they fight or sit helpless in a dead machine. In January 1945, during Operation Nordwind, the 10th SS Panzer Division captures 12 M4, A3 Shermans at Hatten and Ritterschaffen, often referenced as Ha-10 or Hattenheim in German accounts. These tanks, taken from the U.S. 43rd Tank Battalion, are formed into the 13th Company of the 10th SS Panzer Regiment. They serve as reconnaissance and mobile reserve vehicles through the final months of the war. Their roles demand long movements and rapid redeployment. German commanders rely on them because they start and move when ordered. A Sherman that arrives is more valuable than a Panther that fails 20 kilometers away. January 1944 brings expanded testing at Kummersdorf. Engineers examine multiple Sherman variants, the M4, the M4A2 with twin General Motors, 6046 diesels, the M4, A3 with the 4GAA VAH variant shows the same core trait, reliable automotive systems built on sound engineering and consistent manufacturing. The M4, A2 diesel impresses particularly. The Soviet Union receives over 4,000 of these through Lend-Lease. German forces capture several during Eastern Front retreats. The twin diesel engine offers performance comparable to gasoline Shermans while consuming less fuel. German designers have experimented with diesel tank engines, but abandoned them due to production difficulties. American factories build diesel and gasoline Shermans side by side without major disruption. In March 1944, General Heinz Guderian, Inspector General of Panzer Troops, reports that Panther reliability has reached what he calls acceptable standards. Engine life now stands at 700 to 1,000 kilometers. Final drive issues have been reduced through design changes and better manufacturing. Within German communications, this appears as progress. In comparison with Sherman performance, it merely closes part of a gap that has existed since 1942. At the same time, Allied bombing intensifies. On the night of April 27 to 28, 1944, 322 Royal Air Force aircraft strike Friedrichshafen Darts. The Maybach engine plant and the adjacent ZF gearbox factory suffered devastating damage. Imperial War Museum records later described this as the most damaging raid on German tank production of the war. Engine and transmission production halts for 6 months. When output resumes in November 1944, quality has declined. Skilled workers have been drafted. Slave labor fills the gaps. Sabotage appears in small destructive acts. Cigarette filters in oil passages, misaligned gaskets, incorrect clearances. Engines and gearboxes leave the factories with hidden flaws. Sherman production faces none of these pressures. American plants operate far from combat, staffed by paid workers under stable conditions. The core difference lies not in knowledge but in application. German engineers understand automotive theory. They design tanks that excel on paper, thick armor, powerful guns, high specific power. Yet they accept fragile drivetrains and complex maintenance as trade-offs. The Panther's 75mm KWKT 42 and heavy frontal armor overload its powertrain. The Tiger's formidable presence demands constant expert attention. American engineers, shaped by decades of commercial competition, designed for production and service. The Sherman's powertrain uses proven commercial principles. Its electrical system includes a backup generator for turret traverse, even when the main engine stops. German crews, accustomed to losing turret traverse when engines stall, can only imagine such redundancy. By spring 1944, German units across all fronts report worsening mechanical problems. Quality declines as materials and labor deteriorate. Spare parts grow scarce. Panthers must travel by rail for long movements. Orders restrict road marches to preserve final drives. Panther recovery vehicles, built on the same chassis, share the same weaknesses. In some formations, 70% of tank losses result from breakdowns rather than enemy fire. Meanwhile, Sherman production climbs. American factories build 49,324 Shermans during the war, more than total German tank production of all types. Thousands go to British Commonwealth forces. Over 4,000 diesel Shermans reach the Soviet Union. Chinese forces in Burma use Shermans against Japanese armor with devastating effect. Every theater confirms the same pattern. Properly maintained Shermans keep running. German mechanics who work on captured Shermans often express surprise. The Chrysler 5.7 multi-bank engine, with 5 linked engine blocks, appears complex at first glance. In practice, it proves easier to troubleshoot than many Maybach engines. The Ford GA-AVA-R is praised for its reliability and power. The General Motors twin diesel, rejected by the U.S. Army as less reliable than gasoline engines, still outperforms any German diesel tank engine. Design margins become another decisive factor. The transmission and final drives, originally specified for a roughly 30-ton M4, with about 400 horsepower, also handled the 42-ton M4, a 3E2 Jumbo WW, with its heavier armor. The same components transmit up to 650 horsepower from experimental engines without major reinforcement. German engineers often view such overbuilding as wasteful. American engineers treat it as insurance and future capacity. By summer 1944, as Allied forces fight in Normandy, German commanders understand that their disadvantages extend beyond individual tank duels. American artillery, air support, and logistics combine with Sherman reliability to create continuous operational pressure. U.S. armored units can attack, regroup, and attack again with minimal mechanical pauses. Panzer divisions must ration movement, calculating the remaining life of engines, gearboxes, and final drives. German special formations also seek American vehicles. The 150th Panzer Brigade, formed for infiltration operations during the Ardennes offensive in December 1944, attempts to acquire captured Allied equipment. Planners want Shermans for their reliability and familiarity to American observers. In the end, the brigade receives only 2 Shermans, and only one is serviceable. Traffic congestion prevents it from reaching its intended objectives. Even here, the choice of vehicle type reflects German recognition of American automotive superiority. On January 23, 1945, the Panzer Commission meets and issues a stark report. It lists roughly 500 defective final drives in Panzer IVs, 370 in Panthers, and about 100 in Tigers before the 1945 Eastern Offensive. Around 200 failures are recorded in the Hetzer tank destroyer. General Lieutenant Wolfgang Tamal, Chief of Staff to Guderian, summarizes the situation. Under such conditions, orderly use of tanks becomes impossible. Troops lose confidence in their vehicles. In some cases, they abandon tanks solely due to final drive problems, fearing immobilization and capture. German armor, designed to intimidate, fails at the basic requirement of reaching and surviving the battlefield. As Soviet forces advance in early 1945, Kummersdorf prepares for evacuation. Engineers pack reports, drawings, and photographs into crates. Some captured vehicles, including at least 2 Shermans, are pressed into improvised combat service around Berlin. They fight alongside Panthers and the last Tigers in desperate defensive actions. Fuel shortages eventually halt all movement. Until then, the Shermans continue to operate as long as fuel and ammunition last. German tanks break down at familiar, disheartening rates. The Journey of War Daddy 2 from Tunisia to Brandenburg encapsulates a larger story. German engineers, working within a system that prizes theoretical excellence, create tanks that dominate specification sheets, but falter in sustained operations. American engineers, drawing on mass production and civilian automotive experience, build tanks that appear unsophisticated, yet deliver consistent performance. Post-war Allied analysis confirms the German wartime findings. Investigators examine destroyed German tanks and find mechanical failures as common as combat damage. Broken final drives, seized transmissions, burned out engines. They trace these failures to design choices, production shortcuts, and maintenance demands beyond the capacity of conscript armies. In the 1950s, as West Germany builds the Bundeswehr, these lessons shape new designs. The Leopard 1 main battle tank emerges with a clear emphasis on reliability and maintainability. Designers study American practices and adopt principles that echo the Sherman: robust powertrains, easy access for maintenance, standardized components, room for future upgrades. The Leopard 1 becomes one of the most successful tanks of the Cold War, serving in numerous armies for decades. The Shermans at Kummersdorf, including War Daddy 2 with its name still visible beneath German markings, have left their mark. The quiet data these vehicles produced, the thousands of kilometers, the logged breakdowns, the comparisons with Panthers and Tigers, flows directly into a new German design philosophy that finally puts reliability where War Daddy 2 had always placed it, at the center. They demonstrate that industrial maturity and practical engineering outweigh isolated technical brilliance. German designers pursue advanced specifications, believing superior technology can offset numerical inferiority and resource shortages. American designers focus on vehicles that can be built in vast numbers, maintained by ordinary mechanics, and kept in continuous service. The numbers tell the final story. The United States produces nearly as many Shermans as Germany produces all tank types combined, while also supplying allies and maintaining a high civilian standard of living. German industry, strained by war on multiple fronts and strategic bombing, cannot match this output or this reliability. A Sherman with a 75mm gun that reliably reaches the battlefield and fights effectively outweighs a Panther with a superior gun that breaks down before contact or demands 3 days of maintenance for every day of combat. A battalion with 80% operational vehicles can execute missions that a battalion with 40% readiness cannot attempt. Reliability becomes the decisive factor in armored warfare. By mid-1943, Kummersdorf's engineers understand this. Their reports describe American advantages in clear technical language. They identify the gap, they cannot close it. German industry lacks the time, resources, and stable conditions to redesign its armored fleet around reliability principles. American industry has spent decades building those principles into civilian life. War Daddy, second 49,000, becomes a symbol of this imbalance. Every kilometer it travels without failure on German test tracks undermines confidence in Panther and Tiger designs. Every successful trial confirms that the industrial war has already tilted decisively. In the end, the Sherman does not win through thicker armor or a larger gun. It wins through movement, endurance, and availability. It is present where and when it is needed. It starts in the morning, it reaches the line, it returns for refueling and goes out again. The engineers at Kummersdorf record these facts in tables and graphs. The officers at the front experience them in broken tracks and silent engines. Between them stands War Daddy II, the captured tank that shows, in steel and oil, how a war of machines is decided not only by design, but by the ability to build, maintain, and keep those machines running until the fighting ends.